Here we'll talk about the modern periodic table, how we classify elements on the periodic table, and how we can represent free elements in chemical equations. So based on the type of subshell containing the outermost electrons, they can be divided into categories. There's the main group elements, noble gases, and transition metals, lanthanides, and actinides. Main group elements are the ones that we've dealt with most frequently, groups 1A through 7A. So here's a periodic table. So the ones that are in gray are main group, and that's what we've dealt with most frequently. The blue and that light green, those are the transition metals. Dark green along the very bottom is the lanthanides. Pink along the very, very bottom are the actinides. And noble gases on the far right-hand side. In dealing with these elements, the outermost electrons of an element are called the valence electrons. They're the ones that are involved in chemical bonding, and that's why we're most interested in these valence electrons. Valence electron configuration is also something that we'll need to deal with. So if elements have similar valence electron configurations, that's kind of the reasoning behind the elements having these same chemical properties. So we've talked about various groups having similar chemical properties in the past, but we've never really talked about why that was. It really is based on these valence electron configurations. So an example of this would be halogens. All of those have the outer same electron configuration. They have NS2, NP5, where N is some integer. So they have 7 valence electrons total, 2 of which are in an s orbital, 5 of which are in a p orbital. And it's kind of because of these valence electrons that all of those halogens have very similar chemical properties. One of the similar chemical properties that we're already somewhat familiar with is that we know that they preferentially have a -1 charge associated with them as an ion. So again, this is what the periodic table looks like, including the outermost valence electrons here, where you can see any given group has similar electron configurations. So group 1 or group 1A, which are the alkali metals, those all have similar characteristics. Those all have just an S1 electron. So lithium is a 2s1, sodium is a 3s1, potassium 4s1, so on and so forth. They all have just one valence electron, and we know that they have similar chemical properties. Again, we know that they preferentially have the same charge associated with them. They tend to be a +1 cation. So because metals typically don't exist in discrete molecular units, we will write them just the same as their element symbol. And again, we're probably familiar with this. We're just going to use, for iron, Fe. It's the same as the symbol of the element. This isn't always true in chemical equations if you are dealing with nonmetals. So some nonmetals exist as polyatomic molecules. A few of them we're already familiar with. So H2, N2, O2, F2, Cl2, Br2, I2 are the diatomics that we're already familiar with. Besides hydrogen, which is its own thing up in the left-hand corner, all of those other diatomics make a little 7 on the periodic table, and that's how you can remember that there are 7 of them total. But there's also a few that are more than 2, like phosphorus in nature exists as P4. Another one that we've probably run into was sulfur as S8. Sometimes we don't represent that. We can also just write sulfur as sulfur, even though we do know that it in nature it is S8. So these are what we should be using in chemical equations, which we're already familiar with that, especially with hydrogen gas, H2. Noble gases, they also exist as isolated atoms. So we treat these similarly to how we would represent metals, for example. Of course, a different state, these are going to be gases, but we'll just write out their chemical symbols. Metalloids also are like metals, so we just represent them also as their chemical symbols.